Welcome back. This is the second part of study session 8. From our previous study, we have seen how we can use differentiation to solve rectilinear problem, tangent and normal problem, maximum and minimum value problem. We are going to continue our discussion on application of differentiation. While you have studied this session, you should be able to calculate the rate of change using differentiation. You should be able to use differentiation to solve curve sketching problem. Now, application on rates of change, that is how to apply differentiation on rates of change. When two variables are being considered and both variables varies with time and they both have a relation between them, we can express the rate of change of one in terms of the other simply by differentiating both sides with respect to time. Now we are going to solve an example so that you can understand what I just explained to you better. Now this example is the seventh example of study session 8. It says a stone is dropped into a pond. The ripples forming concentric circle which expand. At what rate is the area of one of these circles increasing when the radius is 4 meters and increasing at the rate of 0.5 meters per second? From the explanation I defined earlier, it said when two variables are being considered. In this question, we have to identify the two variables being considered. And the variables are the area and the radius. Now it says we are going to differentiate the two variables with respect to time. That means we are going to differentiate the area with respect to time, and we are going to differentiate the radius with respect to time. From there, we can find our answer, which says at what rate is the area of one of these circles increasing when the radius is 4 meters and increasing at the rate of 0.5 meters per second. Now, let's solve this particular problem. Now, from the question, the formula for the area is going to be pi r squared. Now, we said we are going to differentiate the two variables with respect to time. Now, change in area with time is now going to be, our pi is a constant, is going to be like this, then the t of the radius. Now, if we find the derivative of this, we are going to have the a dt is now going to be 2r pi d half dt. Now, this is going to be our rate of change, which is given as 0.5 meter per second. Now, from the example, I said our half is going to be 4 meters and the half dt is 0.5. Now, if we substitute this into the a dt, we are going to have 2 multiplied by 4 multiplied by 0.5 multiplied by the value of pi, which is going to give us 12.56 meters squared per second. That is our change in area with time. Now, let's continue. The next one we are going to be discussing about is the application on curve sketching. Differentiation can help to find important points on curves, such as the intercepts, the maximum and the minimum points, and the point of inflection. When we say the intercept is where the points meet at this particular point. The maximum and the minimum points. Maximum points in the case of having something like this to the positive side, and minimum points is something like this to the negative side of a graph. And the point of inflection is a point where the curve begins to bend. And in a situation like this, to find the maximum and the minimum point, that is our first derivative for the expression, for the function of y given, and the point of inflection is going to be our second derivative point. So let's solve an example so that you can understand this better also. Now, example 8, it says we should sketch the curve and show intercept, maximum and minimum points, and points of inflection of the expression given, that is y equals x raised to the power 4 minus 6x squared. Now, from this expression, we are going to determine our point of intercept, our maximum and minimum point, and point of inflection. And we are going to use a graph to show how this is being represented when we have calculate all these values. Now, let's solve this example. Now, we said our y is equal to x raised to the power 4 minus 6x squared. Now, in order to find our point of intercept for x axis, now we are going to expand this expression. Now, in expanding the expression, we are going to have our x squared to be, this will be x squared minus 6. Now, if we expand further, we are going to have to be x minus square root of 6 and x plus square root of 6. Now, if we multiply this by this, we are going to get this. And from this, in order to get our x-intercept, say when our y equals 0, the x at point 1 is going to be 0, that is this x squared is going to be 0, and the x at point 2 is going to be square root of 6, that is this point, and at this point our x is going to be square root of minus square root of 6. Now, we have gotten three values for our point x. Now also we are going to get values for our point y, so that we can get our point of intercept. Now, in order to get our value for point y, we are going to substitute all this value of x into expression y here, so that we'll get our x. So when our x equals 0, our y is going to be 0 raised to the power 4 minus 6 into 0. That means our answer is going to be 0 for y. When our x equals square root of 6, our y is now going to be square root of 6 raised to the power 4 minus 6 square root of 6 squared. So our value of y is going to be 0. This will be 36, and this will be 36 also. 36 minus 36, we are going to have 0. And also, when y equals minus square root of 6, when x equals minus square root of 6, our y also will be 0. When you substitute square root of 6 into the point, we are going to have 0 also. Now, the next one is to calculate our maximum and minimum points. Now, to calculate the maximum and minimum points, recall that I told you that the maximum and minimum point is the first derivative of the expression, and the expression is y equals x raised to the power 4 minus 6x squared. Now, the first derivative of this is going to be 4x raised to the power 3 minus 12x. That is our point. Now, in order to now get the maximum and the minimum point, we are going to expand this expression. Now, if we expand this, we are going to have our 4x to be x squared minus 3. Now, if we expand further, we are going to have our 4x is going to be x minus square root of 3 and x plus square root of 3. So from here, when our dy dx equals 0, we are going to have our x to be 0, and for the first value of x. The second value of x, that is, we are going to have value for this, this, and this. The second value of x, we are going to have our x to be square root of 3, and for the third value of x, our x is going to be square root minus square root of 3. Now, in order to find the point y for this expression, we are going to substitute this value of x into this expression, just like we did in the first calculation, that is when we are calculating for our point of intercept. So when x is equal to 0, our y also will be 0, and also when x equals root 3, our y is going to be minus 9. And finally, you know, when you substitute the value of root 3 into this expression of y, you are going to get minus 9. And finally, when our x equals minus square root of 3, our y is going to be minus 9 also. You know, you substitute the value of minus square root of 3 into y, then you find the value of y. Now let's proceed. The third point we are going to find now is a point of inflection. Now recall that we said our point of inflection is the second derivative of the formula. You know, we said of the expression, rather, we said the first expression is y equals x raised to power 4 minus 6x squared. Now we find our maximum and minimum points using the first derivative, which is 4x raised to power 3 minus 12x. Now the point of inflection now is going to be the second derivative, which is the square y dx squared, which is now going to be our 12x squared minus 12. So it is this one that we are now going to use to calculate for our point of inflection. Now, in order to calculate the point of inflection, we are going to expand this further. Now, if we expand it further, we are going to have our 12 into x squared minus 1. Now, if we expand this, we are going to have 12 into x minus square root of 1, x plus square root of 1. And you know that from this square root of 1 is 1, so we can as well say 1, 1. So I hope you understand what I just did. So from here, we are going to find the true value of x, which is x is going to be 1 and x is going to be minus 1. Now if we substitute this value of 1 and minus 1 into this expression, so we can say when x is 1, our y is going to be minus 5. And likewise, when x is minus 1, our y also is going to be minus 5. So this value of x and y that we have gotten is what we are now going to use to plot our graph, which is going to be shown to you now. Now, from what we have solved, you know, we are going to have our point of intercept. If you follow it wholeheartedly, that the first point is 0, 0, that is x equals 0, y equals 0. Then the second point of intercept is at minus square root of 6, 0. And the third point is at minus square root of 6, 0. Now, the maxima and the minima point here, the first point is at when x is 0 and y is 0. The second point is when x is minus square root of 3 and y is minus 9. And the third point is at when x is square root of 3 and y is minus 9. Likewise, the point of inflection is when x is minus 1 and y is minus 5, and the second point is that when x is 1 and y is minus 5. This is shown on your screen. Now the point of intercept, we said the first point is when x is this at this point we have 0, 0. Then the second point here is when x is minus square root of 6, 0, and the third point is here when x is square root of 6, 0. Those are the points of intercept. The second point is the maxima and the minimal points. The first point for maxima and minimal points is here also when x is 0 and y is 0. The second point is here when x is minus square root of 3 and y is minus 9 rather, and the third point is here when x is square root of 3 and y is minus 9. Then the next one we calculated is the point of inflection. So the first point for inflection is here when x is minus 1 and y is minus 5, and the second point is here when x is 1 and y is minus 5. You can see that this is a very simple mathematics. It's very simple. This is one of the ways you can apply differentiation in solving a curve sketching problem, and from here you can see the graph we are able to get. Now we have come to the end of this study, but before we go, let's do a quick summary of what we have learned so far. We have seen how useful differentiation is in solving real-world problems. We have seen its application in solving rectilinear problem in the first part of this problem, and also in solving tangent and normal problem and maximum and minimum value problem. And in this particular study session, we have seen how we can use it to solve the rates of change, and we have seen how we can use it to solve curve sketching problem. You can read through your study pack to complement your knowledge about the subject discussed in this video, so that you can have an elaborate understanding on application of differentiation. Thank you for listening. See you in the next class.